All right, welcome to a quick video here where I want to talk a little bit about random number generators, sometimes also known as pseudo-random number generators, and I'll maybe comment on a little bit why they're known as that. To start out, I want to maybe just talk a little bit about what the notion of random means. So in natural language, we use the word random to describe all kinds of things. That person can be random, but all kinds of things can be described as random. And then maybe on the other side of that, in another vein, we might say, well, what kind of tools do we use in the real world to generate randomness if we need it? So sometimes we think of randomness as a resource. So how do we generate some of that if we need it? And of course, coming to mind might be a few places where we use randomness in games. Maybe you can just flip a coin if you just need a random bit, a heads, a tails, a true, a false, a yes, a no. Or I'm a Dungeons and Dragons player. I play lots of Dungeons and Dragons. I like to roll dice, different sided die. Of course, the most common one is a 6-sided die used in all kinds of games, Monopoly, craps, all kinds of things. And then another tool we use to inject randomness into our games are a deck of cards. We can shuffle them, put them into a different order, and then every time we play the game, if the deck's in a different order, it's going to produce a different game and enough variation, and it's going to be interesting for us to play. So these are all examples of tools we use to generate randomness, and we might think of these as random items that have randomness in them. Now, I can expose for us a little bit what randomness kind of means for us if I pose a little bit of a thought experiment here. So imagine that there's a robot that could take a 6-sided die and toss it and have it land on whichever side it wanted. Its knowledge of physics and force were so good that it could just always toss the die and make it land however it wanted. Now, the question I pose here, would you want to gamble with this robot? Probably not. You're going to lose a lot of money if you do so. And the purpose of this thought experiment is to expose that maybe there's something about that die. It's not really that random. In this sense, it wouldn't be random to the robot. And once we know the robot has this skill, the die is no longer random from our perspective. We know the robot can cheat. And so one thing that sort of comes out here is that what makes this a good tool to generate randomness is that we are uncertain of the outcome. We do not know what the outcome is going to be. Once we change that, once we inject the robot and now we can add some certainty about what the outcome is going to be, we no longer think of that as a good tool of randomness. So I want to focus primarily on this idea of uncertainty first and foremost. So uncertainty, where does that come from? So as we saw with the die, sometimes our uncertainty is just due to some ignorance. There is a specific set of forces and contacts the die will make as it rolls across the table before it lands on one of its sides. But if you're a robot who can maybe calculate that very quickly and rapidly and have very high precision tools to observe, then you may not have any ignorance about that outcome, and therefore there's no uncertainty involved in it. Now there are other events where it's possible that uncertainty is completely unavoidable. One area, at least in modern physics, that we think this is true is in quantum mechanics or in quantum physics, where Heisenberg's uncertainty principle states that there are certain facts about very small things, electrons, photons, and so on, that we will always and forever be uncertain about, always have a little bit of puzzle to the nature. And then beyond this barrier, beyond the quantum barrier, there are things that we probably can know nothing about. And so because built into our physics, into our science, there are some natural sources or natural fonts of uncertainty, we also think of these areas as natural sources of randomness. So if we can never be certain about the state of a particular quantum particle, we might be able to look at it and treat it as though a real world coin flip. A real world coin flip, I mean, in a way that an actual coin flip doesn't pass the test, because skilled flippers or skilled robots might be able to manipulate that tool in a way to eliminate the uncertainty and therefore eliminate the randomness. Now, as far as our science is concerned, as far as our physicists and chemists are concerned, we don't think that's something that's true about the quantum particles. That is, we believe this is built into the physical nature of the universe, and as a result, this uncertainty or this randomness is true or pure or the real randomness. Now, I'm not trying to engage in a philosophical debate here. Is randomness real? If it is, where does it exist? And so on. That I'll leave that to philosophers or a philosophy video. This video is more about how we try and capture randomness in a computational setting, and this discussion of uncertainty is mostly just to allow us to understand that what we treat as random in our normal day lives in the normal world are usually things that we are uncertain about. And there are many ways we could be uncertain about something, but if we are uncertain about something, and more to the point, if we can somewhat be guaranteed that we are uncertain and everyone else can be uncertain about that same thing, then that thing might appear random to us. So another good example of that might be just weather patterns. To a lot of us, say that are not meteorologists, weather patterns maybe appear a little bit random. And that's just because we have a lot of uncertainty involved. And again, if you were the type of scientist, the meteorologist that studied weather patterns, you might know enough about them to say, hey, they aren't random. You eliminate that uncertainty and all of a sudden they are no longer random. But for most of us, betting on whether it's going to rain tomorrow or not is really a bet. It's an uncertainty. All right, so the purpose of a computational random number generator is to generate random numbers. And at the very base level, we can think of these as just generating random bits, zeros and ones. So if we want to generate a random integer, we usually do that by generating random bits along the way. But there are other ways that we can do that. And so here I've got a collection of sequences of integers. And the question here is just which ones are you uncertain about the next integer in the sequence. And maybe a quick scan, you can see, well, the first one's pretty obvious. The second one here looks like we have powers of 2, so we can probably predict the next one there. Then perfect squares, so again, probably can predict the next one there. The next list is not sort of a set of well-known numbers, but there is a pattern. So again, we might be able to predict that one there. The next one, again, maybe not perfectly able to predict the pattern here, but I'm going to say, if I have to make a guess with a high probability, the next number is a 1. I don't know, that's my guess. But then the last sequence of numbers, I just crafted them. I intended them to kind of look random. I didn't have a pattern that I was following. I was just sort of picking them out. Although I guess the first three kind of went 3, 6, 9, 2, 5, 8, 1, 4. Does this have a pattern? Okay, so I'm giving you a hint. I did form this. I set it random, but it doesn't really seem random. If you can tell me what that next number is, then you will have exposed what I did to come up with this sequence of numbers. And in fact, if you can figure out what the next number is, then I want you to tell me what the next 2 numbers are. All right. If you do, then you might be able to know what this sequence of numbers are. But all of these numbers might have various degrees of uncertainty as to knowing what the next one is, depending on how much you know about math and patterns. But all of them could appear random maybe to someone who has some uncertainty. Now our goal is to craft a sequence maybe like this last one that appears random, at least at first glance, even if under the surface, like this one, it is not random under the surface. So to do this, typically what we're going to do is first we're going to need to rely on the fact that inside of our machines, inside computers, we don't actually have any circuit that generates a random bit. We don't have a little quantum qubit in there that we can just observe that will tell us a 0 or a 1 perfectly at random. And because we don't have that, we have to have some tool using only the tools we have available within our machine to generate this randomness. And here's the main problem. Our machine is 100% deterministic, meaning the sequences of steps that it's going to be carried out are 100% determined by the program you are running and the input that you give it. You cannot change that sequence in any way, meaning if I ask it for a sequence of random numbers, every time I ask it, it will give me the same sequence of random numbers, as long as we are relying 100% on the deterministic nature of the machine. If we want to break the machine out of this 100% deterministic realm, we need to find some randomness and inject it into that deterministic process somewhere. We need to go in there and somehow find pure randomness, that's where our philosophical discussion came from, and inject it in there. Now, where's pure randomness? Where can we find it? Well, in our world, we can find randomness in things that are uncertain, things that we find uncertain. So that means we want to find some source of randomness in our environment that we find uncertain. We're going to use that to start off our random sequence of numbers because that's the randomness. And then even if we process deterministically after that point, hopefully the numbers that come out will preserve that randomness and appear random to us. So one of the oldest methods for generating random numbers is called a linear congruential generator. And this generator is 100% deterministic, with one exception is we rely on a seed. We give it a seed, and the goal is for that seed, that initial seed, to be random. And remember, our understanding of what it means to be random here is we want to have uncertainty about that seed. We want it to be something that we don't know, or it would be hard for us to predict. Where we find that then typically is we're going to go to our CPU, and inside our CPU is a clock, and that clock counts from 0 to some really large number over and over again, overflowing, resetting to 0 whenever it gets to the top, and it's just counting the number of operations that the CPU is executing one at a time. Now what we're going to do is when it becomes time for us to start generating a sequence of random numbers, we usually at that point reach out and grab the clock tick, whatever it is. Now remember, this is going to be some number between 0 and some really big number, say 2 to the 32 if it's a 32-bit clock. So then we'd have some number between, about 0 and 4 billion, and that number is pretty hard to predict. In fact, if you don't know any better what the current clock tick is, then it could be any number between 0 and about 4 billion with equal probability, because at any one point your machine is chugging through those ticks and is going at a specific rate, so each tick has a uniform chance of showing up when you query the clock and ask it for its value. So the very conventional seed for most random number generators and in most computational settings is going to be the current clock tick when we initialize that random number generator. Now, because of this, it becomes critical for us to understand that we really only want to initialize the random number generator once. So what this means is if you're working in a program, it's not very good practice to make a bunch of different random number generators, each one, say, being handed out to a specific object in your program. The reason for this is by accident, you can get those random number generators tied together, so they both end up going in the same lockstep, maybe both giving you the exact same numbers or same pattern, and therefore making it making strange occurrences happen in your program when you would otherwise think it's randomness that's occurring there. So best practices when using a random number generator in your program is to use one single random number generator. And depending on what kind of programming environment you're in, either leave it as a global, if that's something that's permitted, or pass it between the objects or hand it to objects as they're being initialized so that all objects share the same random number generator. That way you can make sure that none of these errors or accidents in sort of two random number generators generating the same numbers or very similar patterns occurring. Okay, so again, the source that we're going to be using, the source of randomness we're going to use to insert into our random number generator is the clock tick. But once we start things off with the clock tick, everything we do after that will be fully deterministic. Okay, so here I have some code for, this is Java code, and this is Java code for the actual Java random number generator that you might find. This is random number generator following the linear congruential generator model and using some particular values. Now let's just look at the random number generator here, rand. This is the number that when you call rand, it's going to give you a random integer value. Okay, and for now I'm going to assume we're dealing with unsigned integers, but we can translate this into a signed integer if you like. You can see in this setup here I've just decided to seed 1, 2, 3, 4, 5, 6, 7, 8, 9 as my seed number, but here's where we would normally grab the current clock tick. We grab that, and often that clock tick is our first random number, but usually we'll put it through the random number generator once, so it's not exactly the clock tick. We've performed it once. But every time we do this, we're just resetting the current seed value. So we've started our seed value at rand. At the end, we're going to return a new seed value, which is the new value after we perform this operation. Right, so let's take a look at this operation. There's not too much to it. It's very straightforward arithmetic. We're going to take our seed, our original seed. We're going to multiply it by some integer a. We're going to add some other integer c on, and then we're going to mod it by some other integer m. Okay, now let's take a quick look. These are the values that are set for Java's random number generator. First of all, we've got our a value here that we multiply seed by to be this fairly large number. Now I'm just going to check here. That's 3, 6, 9. So we've got about 25 billion here. Now this number, I don't know where they got this number, and I'm going to guess a little bit about it. But first of all, because it's 25 billion, this number does not fit in an int. It fits in a long, though. And most of these operations here are probably going to be performed on longs, not ints, like I have here. Now it is going to return an int, but these are probably going to be performed in longs because we want to maintain the overflow, and we'll see why here in a second. So we take our seed, which is any number in our range, multiply it by this a, which is a large number outside of our range. Okay, our range, remember, is 0 to 4 billion. So outside of our range, we multiply it. So now we've got this really enormous number. Okay, really enormous number. Now also you'll notice this number a isn't just 25 billion. It's 25 billion and some change, where that change at least ends with a 7, meaning we know it's not even, we know it's not divisible by 5, and I bet you, with high probability, you could go double check this if you like, this is probably a prime number. And the reason is multiplying our seed by this prime number is going to give us a better pattern afterwards. And pattern here, I mean more likely we're going to get more randomness in our bit pattern that we get afterwards. So this is a prime number. Now this one I can guarantee you C is a prime number. And that's the one we add on here. Okay. Now we might notice something here, that when we do this, we've got ourselves this large number. We've flipped a few bits at the end. Now when we flip those few bits at the end, that could trigger a carry and flip a few bits further on as well. Okay. But after we do that, we do this mod 48. And maybe to get to see what's going on here, I want to just maybe take this to the side here. Okay, so say we have our long here, and our long we know is 64 bits long. Okay. Now remember, what we're trying to generate is an int, something that's 32 bits long, a random int. And so far what we've done is we've taken an int that's 32 bits long. We've multiplied it by our a, which was 25 billion, which was more than 32 bits long. And so we've now got something that's potentially 64 bits long, or larger. It may have overflowed our long, but remember, we're performing all of our operations in the long. Then, so after we did this operation, we added on our c. Well, that was just 11, so that maybe trickled a overflow through our bits, but you can imagine it flipping a bunch of the bits as it went along. Okay. And then we did our mod, and this is where we did 2 to the 48, sorry, 2 to the 48. Okay. Now 2 to the 48 means, when we do mod 2 to the 48, it means we just chunked off these bits here. We jumped that, we truncated them off. Okay. And it left us with the lower order 48. Right. Now, normally when we do something like this, our output we wanted 32 bits. So normally, instead of doing this, we would mod by 2 to the 32. And that would give us this lower order 32 bits. Now, the reason why Java does something different is Java these operations here are going to actually cause more randomness in the middle order bits than they're going to cause on the low order bits or the high order bits. And so Java wants to keep the middle 32 bits out of our 64 bits, not the lower 32 bits. So that's why at this stage it does mod 2 to the 48, and then before it actually returns the value, it's going to go ahead and do a div 2 to the 60. Okay. Now div here, integer division, is going to truncate off these bits. Okay. Leaving us only with the middle 48, which are thought to be the most random of the bits that we've created. Okay, so again, after this step, after doing these calculations and pulling out those middle 32 bits, that's going to be our new seed value, and that's what we're going to return back to the user. Now, of course, hopefully that's a very randomized number. Now, we as the users often then go and mod it even further, do more things to it. So if we are asked for another random number after that, we keep applying this process over and over again. So after the initial seed, every random number after that is deterministically generated. Meaning, if you know what the initial seed is, you can know what all of the random numbers that come afterwards are. Now, this can actually be useful for those of you who maybe have experience either in gaming or in modding or random generation of environments. Know that sometimes someone in one of these communities might post what they say is the seed of their environment or their game or whatever it might be. And what they're telling you there is that they used a random number generator in their game, and if you want to have the exact same experience that they did, following the exact same random choices they did, then you can plug in this seed that they used, and that will seed their random number generator, and now you will have a very predictable outcome to the continued evolution of your game. Now again, in some games you might say you might want to preserve the random number generator from save games. So if you save your game again, you're still using or save and reload, you're still using the same random number generator. Again, there may be reasons to do that, or there might be reasons to want to reset the number generator after you load to get a fresh new set of random numbers. Either way, there are many games and again random environment generators where the seed becomes an important part of the way that program operates. And if that is the case, then usually you will see somewhere that will advertise what the seed is and then give you an opportunity to enter your own seed if you want to. All right, so I did want to conclude here with just a quick sequence of random numbers that I here have generated myself. Now, this sequence here is one that I generated not using a random number generator, but instead using some uncertainty that you might have in your environment, but I don't have in my environment. So these are not random numbers to me. All right, so this sequence of random numbers here is actually a sequence of numbers that I generated. Now I might claim to you, I could lie, and I said I went to my favorite random number generator. I don't know if you have a favorite random number generator, but mine is at random.org. Head over there and they'll generate random numbers for you. So maybe that's where I got these random numbers. I generated them there, but I didn't. I lied about that. I generated these with my brain. And if you want to know how I did this, I might say that these are all numbers, random numbers in the range 0 to 31. And say you wanted to generate numbers from 0 to 31. Well, there's an interesting data set that has numbers from this range, and these are days of the month. So every day of the month is in the range, well, not 0, we don't have any of those, but 1 to 31. So if I wanted to generate numbers in this range, I could just somehow randomly pick days of the month. Now, how do you randomly pick days of the month? Well, what I did is I took just people that in my family, and I just put them in order. I just sort of went through them and picked out their birthdays. So this is my grandma. She's born on August 11th. And this is my father, born on February 4th, and my mother on December 21st. And here's me, and my sister, and so on, my aunt, and so on. Various members, nieces, nephews, cousins, and uncles. All here, their birthdays just listed in order, not in any specific order, but the order that I thought of them, and that number, that sequence, then appears random to anyone who doesn't know where it came from. And now, what I'm going to do, because this is sort of my personal random number generator, I'm going to preserve my seed throughout this sequence of videos. So whenever we need some random numbers in this sequence of videos, I'm going to pull this sequence of numbers out and use them in our example. So that'll be our random numbers. And so I'm going to go ahead in my next video and use these random numbers in my first exercise to put them into a binary heap, a min heap, one at a time. So please stay tuned. Thanks for watching this video, and we'll see you in the next video.